Fine. Good evening, children. Hope I'm audible to all of you. Yeah. So welcoming, all of you to another session. So we started solving questions based on the chapter work, energy, and power. So that is what we have been seeing so far, and now we'll continue with questions as the difficulty levels. I'm going to little reduce because last time the question was advanced question which we saw. So this time I've picked up easy to moderate questions, and then we will increase the level of toughness gradually. That is what I've planned for the day. So here is the first question on screen. It would be great if one of you can volunteer and read the question and tell me what is given in the question.
Can I go,
Yeah.
sir?
Yes. Please proceed.
A mass of 0.5 kilogram moving with the speed of 1.5 meters per second on a horizontal smooth surface collides with the early weightless spring of force constant K equals 50 Newton per meter. The maximum compression of the spring would be.
Yes. So here they're asking us the compression of the spring. Now, even before we approach to solve the question, now based on the question that is given here, can you tell me the given data appropriately? What's given in the question?
An object with mass 1.5
Yes.
kilograms is moving.
Yes.
Yes, sir.
Okay. So mass is given 0.5 kgs, and that is in proper units. We need not go for conversion because all of you are aware that the SI unit of mass is kilograms, and that is quite appropriate. And then you have speed. They have also given you the speed, or to be more precise, what velocity? It is initial velocity because they're saying the object is already moving. You don't have information that it is moving from rest. They have not given a condition here. They're telling you that the object is already moving with a speed, and that is quite evident from the picture. You can see there is an arrow mark which depicts that it is in motion, it is not at rest. So initial velocity is 1.5 meters per second, and they have also given you spring constant K, which is 15 newtons per meter. I hope this part is very clear to all of you. When you read a question, what is the given data? First and foremost, just take a pencil and just underline what is given, so that you can start working on the solution. All right. So these are the three parameters which are given, three sets of data that we have on the screen. Okay. So they're asking us what is the maximum compression of the spring. So compression of the spring is what they're asking. So how can we approach this question? Anybody? Is any formula striking you? You can let me know. How can we find out the compression of the spring? It's okay even if you do mistakes. You're here to learn. Yes. What's happening as the ball or the object is moving? You can see that spherical ball is moving. So what is the energy that it possesses? Yes, an object in motion would possess what kind of energy?
Kinetic energy.
Exactly. So what's happening? There is transformation of energy taking place. As an object is moving and it's going to hit a spring, okay, which is stationary at an end. So what energy is getting converted to what? That's how you're supposed to think. So kinetic energy of the ball is getting converted to what? The spring is also going to get compressed, right?
Compression energy.
So the compressed potential energy of the spring. Yes, that's correct. Okay, because the size of the spring is going to change, isn't it? Whenever you have a sphere that is going to go and collide with the spring, now you can see that the spring is going to get compressed. Okay, so therefore its length would change. Now that is the virtue of position of the spring is going to change, which means there is a change in potential energy. So kinetic energy is getting converted to potential energy in this case. So it's basically transformation of energy which is taking place. So what is the formula that we can use? According to the work energy theorem. So we apply work energy theorem here. Okay. So work energy theorem is applied. So according to work energy theorem, you can say that the kinetic energy of the ball is getting converted to the potential energy, stored potential energy or elastic potential energy of the spring. Okay. So I am writing it here. Fine. So now we substitute the formula for kinetic energy, which already you guys are aware of. So kinetic energy has got the formula. Anybody? Would you like to tell me the formula for it?
Sir, half into m into v square.
Very good. Half mv squared. So half mv square is equal to elastic potential energy. Yaraj ko terima? You can try. What is the formula for elastic potential energy? In terms of the spring constant K, it is half kx square. Okay. This is the elastic potential energy of the spring. Now here, what are they asking? They are asking us x, the compression. So you would go for a rearrangement, simplify it, and then get the answer. You can see that both the sides half would get cancelled off, right? So what is x equal to? Go for a rearrangement, take an under root. So it is m times v square upon k, isn't it? Under root. So substitute the value, simplify, and get me the answer, children. Tell me what is the answer that you're getting after you substitute and simplify. M is 0.5, which can be written as 5 into 10 power minus 1. V squared, that's which is 1.5 squared. Okay, so 15 squared is anyways, I think you guys know. The square of 15, what's the square of 15? 225, right? Times 10 raised to minus 2. Okay, upon k is also given as 50. Now just you need to go for a simplification. 5 tens are, then you can that 15 square you can take it directly out. I will not expand it also. That comes out as 15 under root of 10 to the power minus 3, and you have a 10 at the bottom, not to forget that, so it's 10 power minus 4. So that comes out as 15 times 10 power minus 2, isn't it? So what's the answer?
Yes, sir.
Yes,
Option A.
correct, which is 0.15 meters. Okay, I hope it's clear. This is how you solve this question. So the answer is option A. Let me just tick it. Okay, so this is the solution for this question, for the first question for the day. Okay, so I hope it's clear, all of you. Anybody's got any doubts, you can ask. Otherwise, we are good to move to the next question. Shall we move on to the next one?
Sir, the potential energy of the spring, how do we get the formula, sir?
Okay, that's it's actually a relation, which wherein we integrate and find out. Last class I taught you work done by a variable force. So using that relation, we can derive the formula half kx square. Now here the formula is necessary for us because you need to remember the formula. Okay, half kx square, because you cannot afford to derive it each and every time. I mean, derivation is quite simple, but still, okay, because it's a competitive approach, so it's better that you can remember it. Okay, so half kx square, where k is the spring constant and x is nothing but the compression of the spring. All right. So that's the idea. Fine. Yes, anybody else, any questions? I hope we are good to go to the next one.
Yes, sir.
Yes, okay, so moving on. Yeah, here comes the next question. Again, I want one of you to read and tell me what's given.
Can I read it, sir?
Yes, proceed.
A wind power generator converts wind energy into electrical energy. Assume the generator converts a fixed fraction of wind energy intercepted by its blades into electrical energy for wind speed v. The electrical power output will be proportional to.
Yes, so the electrical power output, it would be proportional to what? Now you can see the options are all in terms of speed. So you will have to find out what is the power of V, okay, that it is going to be proportional to. So for that, you will have to build in a relationship of power in terms of speed V. So that is what you're supposed to do. Okay, so what's the formula that relates power and a speed V or velocity V? That's how you're supposed to think. Okay, and then you'll have to get the answer. So that is the approach. So anybody the formula for power in terms of speed? Any idea? Otherwise, we can, I can show you how to derive it also, because it's that kind of an approach. Yeah. Does anybody remember the formula that relates power, velocity, or speed and force? Yes. No idea. Okay, I'll tell you. So here we need to make use of the relation power P is equal to, it's a product of force and velocity. Okay, of force into speed. This is the formula for, power. But now it's quite early to decide that, you may be thinking the answer is A, but it's not A. Still, you need to go for an expansion, expand force. Again, you can express force also in terms of speed. That's quite possible. Okay. So how can we express it in terms of velocity? How do you express force in terms of velocity? Yes, anybody? Can you write force as mass into acceleration from Newton's second law? I hope that's how you express it, isn't it? So we can write it as ma times v, where force is mass times acceleration. Let me just put it here within brackets, where force is a product of mass and acceleration. All right. Now, how can we write acceleration in terms of velocity? I hope that's also quite possible, isn't it? What's the formula for acceleration? Can be written as change in velocity upon time, which all of you are aware of. So we can write acceleration as change in velocity. Delta v times v would give you delta v squared upon t. Okay, so we can express it like this. Fine. So this is one relation that we have got. Okay. So this is one. And you also have mass. Now, can we write mass also in terms of density? I hope that's also quite possible, isn't it? So how do you write mass in terms of density? You know that mass m can be written as density times volume. I suppose you guys know this relation, isn't it? So we can write mass as density times volume. Again, I can write volume as area into height. That's also quite possible. So area into height, h. So this is also quite possible. Okay. Or I can write area into displacement. Let me put it as displacement. That's quite appropriate. So I can write rho as. So I would go and substitute in the place of m. I'm going to substitute rho into a into s. And ultimately, I would be getting the relation rho a s times delta v squared, okay, which can also be written as just v squared upon t. Now here, can you see there is another velocity term hiding, which is displacement upon time, isn't it? So displacement by time is velocity again. So finally expression would be rho a delta v cube. So therefore, you can write, you can see that power is proportional to v cube. Okay, because density is constant and area of cross section also would be constant. So this is the relation that you can establish, and therefore the answer is option C. Is that clear? This is how you find out the correct relation between power and velocity. Okay, I hope this is clear. Any doubts you can ask. This is again based on the relation between power, force, and velocity.
Sir, the mass, can you please explain that thing
Yeah.
again?
Yeah, definitely. So mass can be written as density times volume, because you know that density is mass upon volume. Okay, so I go for a rearrangement. And after that, I've expressed volume as area into displacement. Okay, now you would have learned in mathematics that volume is base area times height. So you get that relation from there. Base area times height. Instead of height, I've written displacement. That's it. Okay, I hope you're getting the connect now.
Yes, sir.
Yes? Yeah. That's it. So that's how you approach this question. It's quite simple. You just need to think, from the perspective of how to relate power and velocity. That's it. So, and automatically things would be in place. So, provided you remember the simple formulas, that's it. Okay. So, I hope we are good to go to the next question. Shall we?
Yes, sir.
Okay. So, moving on to the next question. Yeah, here comes the next question. So, yeah, let me read the question for you. Two bars of masses. You have M1, 4 kgs. So I'm underlining the given data here. Let me underline. So the first mass is 4 kilograms. Second mass is 8 kilograms. Okay. They're connected by a non-deformed light spring. Okay, which rests on a horizontal plane. So okay, it's connected to a non-deformed light spring which is resting on a horizontal plane. That's what they have shown here in the picture or the diagram. The coefficient of friction between the bars and the surface is 0.2. So they have given you the coefficient of friction mu as 0.2. Then the minimum constant force that has to be applied in the horizontal direction to the bar of mass m1 in order to shift the other bar. So what's the minimum force that you will have to apply to shift the other bar? That is the other bar m2. That is a question. Okay, so it rests on a horizontal plane. You can see that there is a force that is acting towards the right on the bar m1. They're asking you what minimum force you will have to apply on m1 so that m2 would just get shifted or it would just begin to move. That's the question. Provided the coefficient between the bars and the surface is 0.2. So we have mass with us, we have the coefficient of friction as 0.2, and we'll have to find out what is F, the minimum force. Okay, I hope you get the question. Based on the question, now you will have to identify what is the amount of force that's required to shift the bar. Okay, yeah, I'll just give you some time to think. I want you guys to brainstorm and just tell me how you would approach this question. You can just take a minute, analyze, and tell me. So, how are you proceeding? How would you like to solve this question? Yes, anybody has got any idea of how you can approach this question? What concept can we use? Is there any equation that you can frame? So how do you proceed with this? Yeah, anybody would like to volunteer? You just need to think a little bit because here you have a spring. You just imagine instead of a spring, if you had a rope, what you would have done. Okay, it's very simple to that. It's very similar to that of a rope case. Instead of rope, there is a spring here. That's it. We have already looked at this, in laws of motion chapter. You need to think from that perspective. You will get the answer. I mean, you will get the idea of how to solve it. Okay, fine. I hope you guys are thinking and you're trying to do it. Okay, you have a piece of paper, or a notebook where you guys are trying it. Okay, so I hope you're trying to get some equation. Anybody is getting some equation, you can tell me so that we'll see, if you're on the right track. You have a horizontal force that is being applied here. That's quite evident. So when you apply a force, now what's going to happen? Obviously, the blocks are going to move, right? It would just be ready to move. The bar M1 would move. So don't you think we are doing work in applying a force on the bar M1? Is work being done or not? Are
Yes,
we
sir.
doing some work? Yeah. So when you say work is done, so what is that force equal to? How can you write that force? Or I mean, how can you write work done in terms of force? Let me put it the other way. Work done is equal to force into displacement. You guys remember this relation, isn't it? So that's the work done on a block. If you want to move a block, or you want to move it from, change its position, or you would like to displace it from one position to another. So obviously you need to apply force, and that requires, then you say that work is being done if the object is going to move. Okay. So from the question, they are telling you that it's going to be shifted from one place to another. Okay. Or you're going to apply a force and you're trying to do work. But when you do work, don't you think there is an opposite force that is also acting? It's a contact force.
Yes, sir.
Yeah. What force is that?
Frictional force.
Exactly. So you're trying to do work against friction. Okay. So when you start solving this, you need to understand that you're doing work against friction. So when you're doing work against friction, so how can we write the relation here for the work done against friction? So I say, I know that work done is equal to force into displacement. Okay, so I'm using that relation first, force into displacement x. Okay, now here frictional force also comes into play, not to forget. Okay, so when you express in terms of frictional force, so how can we write this relation as? Frictional force can be written as mu into n, right, where n is your normal reaction. Okay, so mu n into x. This is a relation I get because frictional force has the formula mu times n. Okay, so we can write it as mu n times x. Now what is n? N is nothing but the normal reaction, isn't it? So downwards the weight, you have mass. So I'm drawing here m1 into g acting downwards. Perpendicularly upwards, you have the normal reaction force that is acting. So we can say the normal reaction is balancing the weight. So this relation would become mu times, the place of n I can write m1 into g into x. Are you guys getting it? That is the work done against friction. Mu m1 gx. All right. So first you have to find out the work done against friction. Now, once there is work done against friction, then what is there? There is also a spring that is attached between the bars m1 and m2. So as you pull bar m1, don't you think the spring is going to get elongated? So what is
Yes.
the energy involved for the elongation of a spring? Just now we learned from the previous question. We have also solved that. What is the work done for a spring in terms of its spring constant? Yes, the elastic potential energy. It's,
By 2kx squared, sir.
yeah, it's 1 by 2 kx squared or half kx squared. Okay, so I'm writing that also. The energy stored in the spring. So we can write that also as half kx squared. So that's one more. Okay. Okay. And this spring is also connected to another bar, M2. So obviously that's also going to move. So everything is going to move with respect to the force applied. So hence we can say that work done in this system, the work done, so let me write it here. The work done is equal to, first one is the work done against friction, so it's the work against friction, plus it's also the elastic potential energy, the work done against the elastic potential energy of the spring. We can simply put it as work done by the spring, because the energy and work have the same unit joules, so I can use that relation here. Simple. So work done has got the formula F into X is equal to work done against friction. Now work done against friction I've already written there, which is mu m1 gx plus work done by the spring is the elastic potential energy that is being stored in the spring, which is half kx square. Okay, simple. Now when the mass, or you can say the bar m2 is going to move, okay, when the spring is going to achieve its maximum elastic potential energy, which is being stretched, obviously the mass or the bar m2 would start moving. Okay, so don't you think the force is going to balance, isn't it?
Yes,
The
sir.
force by which it is going to move, the block or the bar m2 is going to move, the force due to the spring is going to balance. Okay, and therefore we can say for the second block, I'm writing the equation for block m2 or for bar m2. As it begins to move, we can say the force due to the spring okay, the applied force is going to balance the force of friction by which it is going to move. So if I'm going to equate these both quantities, what do I get? Force due to the spring, as per Hooke's law, I think you guys are aware, it's work done is equal to force into displacement. Let me put it that way. So F into X is equal to force of friction on block M2. For M2, force of friction, I hope you guys are aware, it is mu M2 into G this time, because it is a second bar. So I change the formula to M2, mu times M2 into G. So you get that Fx is equal to mu M2 into G. Okay, so now I go and I'm going to relate, substitute the value in the first equation. So let me name this as equation number 2, let me name this as equation number 1. So putting 2 in 1, and I'm going to simplify, and you will have to find out what is the force that is required. Simple. So go for a substitution, simplify and find out what is the force. That's what we need to do. Okay, so substitute and tell me what are you getting. Substituting the value of kx from equation 2 in equation 1, now what do you get? You get force F is equal to, I can take mu, I can take G also as a common out. So inside the bracket, what can I write? Can I write m1 plus m2 upon 2? You take a common out, x is anyways going to get cancelled off. Okay, because I'm substituting for kx, that's also being eliminated in the process. So this is what we get. Now you substitute this and tell me what's the answer you're getting. Mu G times m1 plus m2 upon 2. Mu is 0.2. G you can take it as 10. M1 is 4, M2 is 8. So how much are you getting? 0.2 into 10 into, within brackets, it's 4 plus 8 upon 2, which is also 4. 4 plus 4 is 8. So 8 times 10 is 80. Into 0.2 is 2 upon 10. Go for a simplification. So the answer is, I hope you're getting 16. When you solve this expression, so you get the force as 16 newtons. All right. So that's how you're supposed to solve this question. Is it clear how to
Yes.
approach? Yeah. So for this, you will have to get the relation. Once you've got the relation, you need to go for a substitution. It's just a substitution method. Substitute and then solve the equations. That's it. So that's the approach for solving this question. Okay, you get the answer as 16 newtons. Let me take the answer. So this is the correct answer, option D. Okay, with that, we'll move to the next question. I hope this is clear. So we'll go to the next question. Okay, so a bullet of mass 80 grams is traveling at a speed of 500 kilometers per hour. So let me just underline the given data. They've given us the mass 80 grams. So mass is given, speed is also given 500 kilometers per hour. Okay, and hits a block of mass 1 kg, which is resting on a frictionless surface. The bullet enters and embeds within the block after traveling 60 centimeters, which is the displacement. They're asking you what is the amount of heat that is being generated. Okay, so the amount of heat that is being generated, so you will have to find this out. Yeah, so you guys can understand the question, the given situation. So what relation can be used here to solve the question? Just you need to think a little bit and tell me how you are planning to approach to solve this. I want all of you to write down, the given data, and then you tell me how you can approach this question. On what basis can we solve it? Okay, the space is actually not sufficient. I need more space, so I'll be sharing the blackboard. I'll show you the solution there. So meanwhile, you guys can just write down the given data. So once you're done, you can let me know. So there is the mass of the bullet being given. You also have the velocity of the bullet, the initial velocity. Okay, I hope all of you have made a note of the given data in the question.
Yes, sir.
Yes. Okay. So I'll go to the blackboard because this question, requires more solving approach. I mean, there is a lot more to solve, and the space is quite insufficient for me here to show. So I'll just show it on the blackboard. So let me start sharing the blackboard. Let me know if you guys are able to see it. I'm just, shifting from here to the blackboard. Yeah, let me know if you guys are able to see the blackboard now. I've started sharing. Yes, are you guys able to see the blackboard?
Yes, sir.
Okay.
Yes, sir.
So, yeah. So in that question, so they're telling you that the bullet is going to enter a block. So as a bullet is entering a block, now what's going to happen? So on what law is it based? It's firing of a bullet. So let me just write it here. So firing a bullet into a rectangular block. So what happens before and after firing? So what is the law that is involved here?
Newton's third law, sir.
Newton's third law. Yes, action reaction force is there. That is also there. One more law. So you have Newton's third law involved. That's correct.
First law, sir.
No, it's not first law. It is the law of conservation of momentum. Okay. So I'll just write it here. It's the law of conservation of momentum. So that is involved. So what do you understand by law of conservation of momentum? It tells you that the total momentum of the system before collision is equal to the total momentum of the system after collision. Okay, so that's the basic idea of law of conservation of momentum. Okay, so momentum before firing is equal to the momentum after firing. That's the idea. So now here, when they tell you that the bullet is entering a rectangular block and it is also being shot with some velocity, so what is the initial momentum of the bullet? Can anybody tell me what is the initial momentum involved? So initial momentum, yeah, of the bullet. This is quite simple. What's the formula for momentum? You know that the formula is mass into, it's the product of mass into velocity, right?
Yes, sir.
Yeah, so mass of the bullet times the initial velocity of the bullet. So initial velocity, let me put it as u. That was given in the question. So what is the mass of the bullet? I think they said it was 80
80 grams.
grams, right? So 80 grams, I'm converting that to kilograms by dividing upon 100 into initial velocity of the bullet. I think that was 500 kilometers per hour, right? I'm converting 500 also in terms of meters per second. So I just need to multiply with 5 upon 18. Okay, simple. Now you simplify all this. Okay, now what do you get? Zeros you can cancel. Okay, and you can also cancel this. 9s are 2, 4s are 8, and 5 5s are 25 times 4 upon 9. So I think 25 times 4 would give you 100 upon 9. So 100 upon 9 would roughly be 11 point. I think you guys are getting 11.1. So it's 11.1 kg. Okay. So the initial momentum is 11.1 kg. Okay, approximately. So we found out the initial momentum. Now, what is the final momentum? Next, we need to find out what is the final momentum after impact. Okay, how do we find out the final momentum? So, formula for momentum, as you guys know, it is mass into final velocity, right? So, now what is the mass that is involved? After the bullet is going to go and embed in the rectangular block, now what would be the total mass? It is mass of the bullet plus mass of the block, isn't it? So therefore, I can write this as mass of the bullet plus capital M, which is mass of the block, into velocity v. Okay. So this is the relation that we get. All right. So now you need to find out what is the final velocity of the system. So you can equate both of them. So here we have two equations. This is the first equation and this is the second equation. According to law of conservation of momentum, don't you think the total momentum before impact is equal to the total momentum after impact?
Yes,
Isn't
sir.
it? So we can equate both 1 and 2. So equating 1 and 2, you get 11.1 is equal to mass of the bullet. Let me substitute mass of the bullet also here. Then go for a simplification. So mass of the bullet 80 grams. In terms of kilograms, I would write it as 0.08 kilograms plus mass of the wooden block. Okay, so what was the mass of the wooden block that was given in the question? Do you remember? 1 kg, right?
Yes, sir.
It was 1 kg. So it is 1 kg times V. So now you need to find out what is V. Just you need to go for a rearrangement. So velocity is equal to 11.1 upon how much is 0.08 plus 1, which is 1.08. Just simplify it, you get velocity. So how much is 11.1 upon 1.08? You just need to simplify that and get the relation. I think you're getting 111 upon 108 cancelling. 10 is there. Okay. I think 10 point something. 10 point. Yeah. Could you please divide and tell me? You would get 10.2 something. Is it 10.29? Go for approximation, isn't it? So you would get the velocity as 10.29. This is the final velocity of the bullet. Okay. Once you've got this, now we need to find out what is the distance traveled by the, I mean, what is the heat dissipated by the bullet. So to find out what is the heat, you need to understand that as the bullet is going, what's happening? There is a transformation of energy that is taking place as the bullet impacts the rectangular wooden block. There is a transformation of energy that is taking place. So what is the transformation of energy? Would anybody like to try and tell me what are the energy transformation taking place as a bullet penetrates inside a wooden block? As the bullet is moving, there is kinetic energy. So what is that kinetic energy getting transformed to?
Heat energy, sir.
Yes, so it's becoming heat energy. Okay. Is it only heat energy? So kinetic energy is getting converted into mainly you talk about heat energy, right? So there is heat energy, and obviously work is also being done because you are firing a bullet. So obviously you're doing work, and that bullet is also moving by a distance inside, right? So that's the basic aspect here. So here we would use the relation that the kinetic energy of the bullet is equal to the total energy. Let me put it this way: instead of just saying kinetic energy, let me say total energy of the system. Okay, so what is the total energy equal to? Let me write it here at the bottom. Total energy here is equal to, yeah, we can say the kinetic energy of the bullet and the block. Of the bullet and the block. Simple. Okay, so that is also there. So that's the total energy. So what we have, plus obviously there is heat energy also which is present. So not to forget that. So that heat energy is purely due to the kinetic energy of the bullet. That is also something that we have to keep in mind. So let me write that as well. Heat energy is purely due to the kinetic energy of the bullet. Okay, so these are the two important relations that we need to know. So kinetic energy of the bullet, you can write it as half half mu squared, which you can calculate because the bullet has got initial velocity. It was fired with some initial velocity. Okay, so half times 80 grams in kilograms, 0.08 times u squared, which is okay, 500 times pi by 18, the whole square. So you need to calculate this. Okay, and you need to relate it. Okay, you go for a simplification, you calculate this expression, you need to evaluate this expression. You would get 771.6. Okay, 0.61. Okay, you simplify this relation, the expression by putting all the values, you get the answer as 771.61. So that's the amount of heat energy. But they're asking you what is the energy dissipated only as heat. There is kinetic energy also involved. Okay, so from total energy, you need to just from this value, you are going to subtract what is that amount of energy that needs to be removed. So we need to subtract something. That is the first value. So let me just write down the amount of energy that needs to be subtracted. That is, we can say final kinetic energy is equal to, now I'm substituting the values, It is kinetic energy of the bullet, which already you have calculated and kept, which we have calculated here above, plus the block. So kinetic energy of the block. So bullet, obviously you have, and block also. So we will be writing it as half m plus m times v square. Half mv square, where m is the total mass. That is something that you guys should be knowing here. So half m plus m, I think we got this value as 1 point something. Let me just check. Yeah, 1.08, okay, into v squared, which is 10.29 the whole square. Substitute, simplifying these values, I would be getting 57.18 joules. Okay, this is the final kinetic energy, which involves both the bullet and the block. Okay, so we only wanted to know how much heat is being dissipated. So what you do, you have to subtract the second value from the first value. You just need to do 1 minus 2. So heat dissipation. We need not require the block value. We need only the bullets heat. So we are going to remove it. So 771.61 minus 57.18. Just go for a subtraction. That would give you the heat dissipation. So how much is that? You go for a subtraction, you get 7, I think it's 714.43 approximately. Okay, joules. So 714.43 joules. All right, so that's how you approach. So that is actually option A, as per our question, which I had given in the previous window. So this is how you approach. You need to remove this value. The final kinetic energy needs to be subtracted from the total energy to get what is the heat dissipation. All right, so this is how you approach this question. Okay, so we'll have a quick recap. So here, when a bullet is being shot into a rectangular wooden block, the question was how much energy is being dissipated as heat. So we find out by applying the law of conservation of momentum along with Newton's third law. So you apply it and you find out what is the final velocity of the bullet that is being shot, which is 10.29. And then we find out the total energy as 771.6, okay, which is purely due to the kinetic energy of the bullet. The initial velocity of 500 kilometers per hour needs to be considered. And then you find out what is the final kinetic energy. We make use of the final velocity of the bullet, which is purely 10.29 and not 500. Okay, and it is the total mass of the bullet plus the block. And then you go for subtracting them. You would finally arrive at the amount of heat that is being dissipated.
Sir,
Yes.
when we are calculating the initial momentum, we do
Yeah.
mass of bullet into velocity.
Yeah.
So we get 80 by 1000 into 500 into 5 by
Yes.
5 by
Yeah, that is actually a conversion formula from kilometers per hour to meters per second. Okay, so 1 kilometer
Yes.
per hour. If you want to convert to meters per second, you apply this formula. I mean, this is a conversion factor rather. It's a factor for conversion because 1 kilometer is equal to 1,000 meters, isn't it? And 1 hour has got how many seconds? It's 3,600 seconds. You simplify this, you would get 5 by 18. 10 upon 36 is nothing but 5 upon 18. Are you getting the logic now?
Yes, sir.
That's the reason I'm multiplying with 5 upon 18. Okay, simple. So that's how we approach this question. I hope this question is clear to all of you. Any doubts you can ask? Shall we move on to the next question?
Yes, yes.
Okay, so moving on, let me share the tab. So I've started sharing the previous tab. So I hope it's visible to all of you. So the answer was A, which I have solved there in the blackboard. So the answer was option A. Okay. Yeah, I think this question we have already done. So it was the answer was 16. So now we are moving on to the next question. Yeah, I want one of you to read. I've got a sore throat, so please one of you can read.
Can I
Yes, yes.
a bucket full of water, a bucket full of weighs 10 kilograms. It's pulled from a well 10 meters deep. It has a small hole from water is escaping at a uniform pressure of 0.0 kilograms per meter. Find the total work done in pulling the bucket full.
Yeah. So they're asking you. So here, what is given? What's the given data? Yeah. What's the given data in this question? Yeah, you
A
have 10
well
kg.
is 10 meters. The bucket is
Yeah. You also have information data about the displacement of height. They've also given you a uniform rate, which is 2 kilograms per meter. Okay, so that's the mass per unit length. That's also given 0.2, which is the ratio of m upon h or m upon l. Okay, they're asking you what is the work done. That's it. Okay, so how we can approach, this question. So for pulling the bucket, so here it's basically the work done. So here you need to find out what is the work done. So the work done here is by a force. So how do you predict your force? Here is what you need to identify. Now water is basically escaping also at a uniform rate of 0.2 kilograms per meter. That is something that is given here. Okay, so water escaping rate, that's given. So let me just write it here. So water escaping rate is mentioned in the question as 0.2 kilograms per meter. That's specified. Okay, now when you try to pull the bucket through some distance, we don't know by how much distance you are pulling. So let us assume that distance that we pull is x. Okay, so let us assume the bucket is pulled by a distance x. So when you assume that it is pulled by some distance x, then what would be the water remained in the bucket as you pull it? So you will have to write the equation for that, because the water in the bucket is not constant. As you pull, the water keeps escaping at a uniform rate of 0.2 kilograms per meter. So by the time you keep pulling it, eventually the water level in the bucket would eventually go down, or it's going to reduce, isn't it? So what is the level of water remaining in the bucket as you're going to pull it? Because you're pulling through a well which is 10 meters deep. So what is the water, remaining in the bucket as you pull it? So let me write that. Water remaining in the bucket as it is pulled, up by, say, here they have given you 10 meters by 10 meters, isn't it? So that is 10 minus the remaining, which is 0.2 x. Okay, because we have assumed that it is being pulled by some distance x, isn't it? So 10 minus 0.2 x kgs, that's the amount of water that is going to remain as you're trying to pull, because the mass is 10 kg. So the amount of water that is going to remain as you're going to pull it upwards, it would be 10 minus 0.2 times x. Okay, x kgs. So we are trying to generalize. Okay, I hope this is clear so far. So now what is the work done in pulling it through a small distance? So work done in pulling it, let me write it here. In pulling the bucket. So how can we express the work done in pulling the bucket through a small distance? The work done can be expressed as force into displacement, as you guys know it. So work done is equal to force into displacement. Now you try to pull it by a very small distance, so I can say dx. Okay, so let me substitute for force. What is the formula for force? You know that force is here mass into acceleration due to gravity. Now why do I say it's acceleration due to gravity? Because you're trying to pull it upwards, and gravity is going to, is a force which is going to act downwards, right? So you're doing work against gravity basically. So it's m into g, right? So mg times x. I will write x as dx. Okay. So why am I writing it as dx? That's because I'm pulling it by a very small distance. Okay. So that's the reason I'm writing it as dx. Fine. So this is the expression that I'm getting. Now I can integrate on both the sides. I mean, you go for an integration and you're trying to pull it until 10 meters. Okay. So we can integrate. Our mass is constant. I mean, mass is not constant, sorry, because here we have expressed mass as a function. Here, m is 10 minus 0.2x. So I need to substitute that in place of n, which is 10 minus 0.2x into g into dx. It's integration from 0 to 10. Okay, are you guys getting it? So this is what needs to be done. Okay, and now you need to go for integration. Very simple. So g can be taken out. G times integration of, say, 0 to 10 times 10 into dx minus, again, so g is common for both, so I'll take the entire common out. Okay, you can put a big bracket, and then we can say 0.2 also common, integration of x into dx 0 to 10, and then close the bracket. So here it's integration, purely integration from here. So can you tell me what happens when you integrate this function? Oh my god, one second, let me go back. Let me just, increase the size. A mistake, I just minimized it. Yeah. Yeah, so now you need to simplify the integration part. Now g is 10. How much is integration of 10 into dx? Dx is x, isn't it? So x, when you integrate dx, you get x. So 0 to 10 minus, again, 10 times 0.2. It is 2 again. Okay, I'm considering the g as well. Okay, so it is 2 times integration of x is x square upon 2, 0 to 10. Simplify it. 10 tens are 100 times 10 minus 0 is 10. So 2 would get cancelled here, and x square is 10 square is again 100. Okay. So what's the answer that you're getting? 1000 minus 100. 1000 minus 100 gives you 900 joules. So the answer is 900 joules. Okay, option C is the answer. I hope it's clear. This is how you approach this question. Okay, you guys got it, or you want me to, you have any doubts, or you want me to explain again? I'll explain.
Can you please explain it again, sir?
Yeah. So here, according to the question, they're asking us to find out what is the total work done in pulling a bucket, provided the bucket has got a hole and water is escaping at the rate of 0.2 kilograms per meter. So given the data, so we are trying to find out what is the total work done in pulling the bucket from a well that is 10 meters deep. You're pulling it from a well that is 10 meters deep. Okay, so initially it is going to be 0, and then the height is going to increase as you pull. So from 0 to 10 would be the limits. Okay, so because water is escaping in the bucket at the rate of 0.2 kilograms per meter, so as you're going to pull by some distance x, the water that remains in the bucket is going to be 10 minus 0.2x. This is the mass that would remain as you're pulling the bucket upwards, okay, by some distance x. So you need to write mass as a function of distance, I mean as a function of the distance that you're pulling it upwards. So m is equal to 10 minus 0.2x. That's the first step. After that, we apply the formula. Work done is equal to force into displacement. Force is mass times gravity because you're pulling it upwards, okay, into dx, because I assume that it has been pulled by a very small distance. Okay, this is basically for integration the integrating factor. You call this dx as an integrating factor. Okay, then I substitute the mass. We have already found out what is the mass that would remain in the bucket as it is being pulled up, which is 10 minus 0.2x. You integrate the limits from 0 to 10 because you're pulling it until the surface. Okay, by the time it comes to the surface, it is 10 meters high from the ground level of the well. Substitute, then you simplify, you need to do integration, and you would get the answer as 900 joules. That's the work done. Okay, so that's the approach to solve this question. All right, so I hope this part is clear. Shall we move on to the next one? The next question. Yeah. I hope you guys are making note of it. You know how to approach these questions. This is quite crucial. You know, you have questions that can come up like this. Okay. So modeling, this is basically, you know, it is related to how to model a real life situation. You know, as water is escaping at a uniform rate. Okay. So you have an idea of how to find out what is the amount of water that's remaining. Okay. So that's the reason it's quite necessary. So here we move on to the next question. Here comes the next question. One of you can read it.
Can I?
Yes, yes.
A fire length 24 meters coiled by putting the end of the hose horizontally along the friction surface at a rate of 2.3 meters per second. The mass of one meter of the hose is 0.45 kilograms. How much is important in uncoiling the hose?
Yeah. So how much kinetic energy is required to uncoil the hose? That's what they're asking you. Okay, they've given you the total length of the hose, which is 24 meters, and it's been uncoiled by pulling the end of the hose horizontally along a friction surface at a steady rate of 2.3 meters per second. That's how it is being pulled. Okay, so the mass of 1 meter of the hose is 0.25 kg. That means every meter of the hose, every cross section, every meter has got a mass of 0.25 kg. So how much kinetic energy is required to uncoil 12 meters of this hose? Not the entire 24, just 12 meters they're asking. Okay. So you need to get the relationship and then you need to solve. So what is the mass of 1 meter? That's quite evident from this question. Let me write it here. So mass of 1 meter is 0.25 kg. Of the hose is 0.25 kg. That's given. Apart from that, the total length of the hose, for us here, you need to uncoil only for 12 meters. So that is the length that we would consider. Okay, for solving, you would not consider 24 meters. You would only consider 12 meters because you need to find out kinetic energy for only uncoiling half of it, not the entire hose. Okay, so the length for us is 12 meters for uncoiling. Okay, so what would be the net mass of the hose for uncoiling? Every meter is 0.25 kg and the length, total length is 12 meters. So what would be the net mass? It would be the total length times the mass of the hose for every meter, which is going to be 12 times 0.25. Are you understanding? For the entire 12 meter, we need to find out what is the cumulative mass. Okay, so it's 12 times 0.25. 12 times 0.25, you would get, I think, 25 upon 100. I think 3 kgs, right? So you get it as 3 kgs. And what is the velocity with which the hose is being pulled? I think that's also given in the question. It's 2.3 meters per second, isn't it? So that's the velocity with which it is being pulled, the uniform rate at which it is being pulled. So what would be the kinetic energy? Formula for kinetic energy, you guys are aware about that, which is half mv squared. Okay, substitute the values. So half times mass is 3 kgs into v square is nothing but 2.3 the whole square. Now go for a simplification. To simplify it, you would get the answer. How much are you getting? I think 7.93. I think 7.935 should be the answer, right? You get 7.935 as the answer. Is it clear? I think this is quite simple, right? So you understand what is given here. Velocity is given, the length is given, okay, and mass for each meter is given. So you find out the net mass, substitute in the formula for kinetic energy, and then you get the answer as 7.935. All right. So the answer is option A. Is it clear, children?
Yes, yes.
Okay. So with that, we move on to the next question. Here there's another question. Okay. The last question for the day. Yeah. Could you please read it?
Can I do
Yes.
a rod AB of mass 10 kilograms and length 4 meters rest on the floor with length A fixed so as to stayed in a plane above perpendicular passing. If the work done to the rod is equal, the height the end base that floor is.
Yeah. So you'll have to find out the height to which the rod is being raised. Okay. So that's what you need to find here. Okay. So for this, you guys need to draw a figure, and you need to solve it based on the figure that you're drawing. Okay. So just draw a figure for assumption, and then you will have to solve it. So you have a rod of AB. Okay, a rod AB of mass 10 kg. So they have given you the data here as 10 kgs, which is the mass. Length is also given. You have length L is 4 meters. It rests on a horizontal floor. Okay, so it is initially resting on a horizontal floor. Okay, now you're applying a force and you try to rotate it in the vertical plane about perpendicular axis passing through A. Okay, that means initially the rod is horizontal. So say the rod AB is like this. And according to this, they have told you that the length of this rod is 4 meters. It's resting on the horizontal floor. And end A is fixed, which means this end is fixed. So that means B is free to move. Okay. So initially the rod is kept on the horizontal floor as shown in the figure. So I'm drawing the figure. Then what are we doing? We are trying to lift point B upwards. Okay. So the floor remains intact like this. After you pull B, what happens? A is fixed. So B is being pulled upwards, as you can see. So A is fixed at this point. Okay. So this point is fixed. And end B is pulled upwards. So as you're pulling end B upwards, you can see that you're raising it to a height with respect to the ground. This is the height, H. Are you getting it? So you can see a right angle triangle is formed. Okay. So center of mass of the rod would lie at this point. Okay, that is at the point of 2 meters. This is the center of mass. So here you have weight of the rod that is going to act with respect to center of the mass, which is M into G. Right? Simple. So that is the amount of force that is going to act. Okay. So mg would act vertically downwards. So how much is that? Mass is 10 kg. So 10 into 10, I think it's 100 newtons weight that is acting vertically downwards with respect to the center of mass. Let's call it point O. I hope the situation is clear so far. So we need to find out what is the height, okay, to which it is being pulled. Okay, they're saying work done by the rod is 100 joules. What's the formula for work done? I hope you guys are all aware about it. So work done is equal to force into displacement. Okay, now the force required to pull the rod by some distance, you can say it is mass into acceleration due to gravity, which we have already found out as 100 newtons. Okay, into now you can say the height to which end B is raised vertically above the ground. So what is the corresponding height to which it is being raised? Anybody? So this point O, so this height, the center of mass. So what is the height to which it is being raised? Just the center of mass point, this point. So this length, total length is height. Height is h. With respect to the center of mass, it will be half of the height, isn't it? It will be h by 2. So displacement is nothing but the half of the height with respect to the center of mass. So here is where most of you would go wrong. You would just directly substitute the height and you would be solving. So this is something that you'll have to be careful about. Okay. So it's h upon 2. So our total work done is 100 joules. That's also given in the question. Now go for a rearrangement. 100 would anyways get cancelled off. So how much is h? H is equal to 2 meters. Okay, so the answer is 2 meters. Fine. So you need to find out only until which the axis is passing through the rod, which means it is only with respect to the center of mass, that point. Okay. So with respect to that point, how far it is from the ground. So that will be half the height to which point B is being raised. Simple. Is that clear? So you get height as 2 meters. So the answer is option B here. Done? Okay. So that's how you approach this question. I hope this part is clear. Any doubts you can ask, okay, with respect to what we have done for the day. Okay. Yeah, anybody has got any questions?
Sir, can you explain the last part of the question again?
Yeah. The part of the question that is with respect to point O. Point O is the center of mass. It lies exactly at the center of the rod AB. Okay. So that is just going to be 2 meters. That is half of the height to which point B is being raised. If you're raising B to a height of h, the center of mass would be at half the height from the ground, which is h upon 2. Okay, that is why I am taking h upon 2 and not h. We need to take h by 2. Okay, because the center of mass of the rod is at a height of h by 2 with respect to the horizontal surface or the ground level, you can call it. That's the reason displacement is h by 2. That's the only part that you will have to be careful about.
Yes, sir.
Okay, yeah. That's it, children. So with that, we come to the end of today's lecture. So we'll wind up. I'll post this notes also in the groups so you can go through it. Okay, so please solve the questions on a daily basis. That will definitely help. All right. Yeah. So meet you guys again next week. Yeah. Okay. Fine. Bye, children. Take